Assalamualaikum. My name is Muhammad Daniel bin Abdullah and my group member is Muhammad Faiz Iskandar bin Johari, Muhammad Amha Fahmi bin Anwar, Tanah Silen, anak lelaki Pebalen, Hari Haran, anak lelaki Sukumaran. Okay, today we want to present about transfer function and dot plot. Okay, introduction to transfer function. What is a transfer function? Okay, transfer function is H omega is the frequency dependent ratio of a phasor output y omega to a phasor input x omega. Mathematical representation H omega equal to y omega over x omega. Okay, purpose for transfer function is a fundamental tool for finding the frequency response of a linear time invariant LTI circuit. It helps us understand how a circuit amplifies or attenuates signals and shift their phase at different frequency. Okay, for transfer function A, we have H omega equal to 200 J omega over J omega plus 2 times J omega plus 10. Okay, to facilitate broad plotting, we convert the transfer function into a standard form where each pole n0 is represented as 1 plus J omega over omega C. Okay, first, H omega equal to 200 J omega over 2 times 1 plus J omega over 2 times 10 uh, times 1 plus J omega over 10. Okay, the next step, we have 200 over 20 times J omega over 1 plus J omega over 2 times with 1 plus J omega over 10. And last form, we have H omega equal to 10 times J omega over 1 plus J omega over 2 times with 1 plus J omega over 10. Okay, for magnitude dot plot, the yellow line is refer to 20 log 10 equal to 20 dB. The green line equal to refer to J omega. The red line refer to 1 over 1 plus J omega over 10, and the blue line is refer to 1 over 1 plus J omega over 2. H omega equal to 10 J omega over 1 plus J omega over 2 times with 1 plus J omega over 10. Gain K equal to 10. So we use the 20 log. So we have 20 dB. 0 at origin is positive 20 dB. Decay positive 90 degrees. Okay, pole at omega equal to 2. We have negative 20 dB and the decay is negative 90 degree. Pole at omega equal to 10. We have negative 20 dB. The decay is negative 90 degrees.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amha Fahmi, and thank you for explaining the magnitude plots. And the second one's still the same equations. I will explain the phase plot. A phase plot in electrical circuits is a graphical representations that illustrates the phase relationship between different voltage or currents in a AC circuit. It uses phasor diagrams to describe the magnitudes and phase angle of these questions. So that we can see H omega for 200 J omega equals J omega plus 2 and J omega plus 10. That we have simplifies J omega which is 10 J omega equals 1 plus J omega equals 2 and 1 plus J omega equals 10. And we have the two equations is for the number ones 20 logs 10, which is the phase is 0. We can see the phase started from 0 and straight run until the 1000s. And number 2 20 logs 10 j omega, which is the phase is 90 degrees, same as the k that start from 0, but the j omega we start from the 90s until the 1000s. And number 3 negative 10 3 log 10 for 1 plus j omega equals 2. We got the phase is 2 that we got from the equations. And the next step is p1 over 10, which is 0.2. And next steps is 10 p1, which is 10 20. This number 3, we plot the first equation, which is 1 plus j omega equals 2, which is 0.2. We start the that we can see in the spots, the colors is the blue ones, and we start from the 0.2 until 20. So the 20, where's the 20s? This is the 20s, and then uh, the graph was going to the 1000s, which is the straight lines. And then number 4, negative 20 log 10, which is 1 plus j omega over 10. And the phase is 10. We got from the equation same as the 3. And for the next step, p2 over 10, which is 1. That we started the graph, which is 1, which the red one was the 1s over 1 plus j omega over 10, which is start with 1s. This is 1 in the graph, and start from the 0 degrees, and the 10th p2 equals, which is hundreds, and then the red one with n until the hundreds. So that we can see for the black ones, that's the final graph that's combine all equations. What is the equation is 1 plus j omega over 2 and 1 plus j omega over 10, that we combine the blue and the red ones to make the perfect last last graph. And then we start from the 90 degrees, and then the two plots we refer to the 1 plus j omega over 2, and then until still a half of the blue ones. And then for the seconds we refer to the red one, which is 1 plus j omega over 10. And then we reach to the 100s, 100s, and then follows, and still going to the 1000s.
Okay, Assalamualaikum and hi. My name is Mahmud Iskandar bin Johari, and in this presentation, I walk you through the process of analyzing board plot and constructing its corresponding G-transfer function step by step. We begin by analyzing the given board magnitude plot. At low frequencies, the magnitude is flat at 40 dB. We then observe two important breakpoints, which is the first corner frequency occurs at omega equal to 100 radian over second. The second corner frequency is at omega 1000 radian over second. Between these 2 points, the plot drops by 20 decibel per decade, which suggests that a single pole is present at omega equal to 100 radian over second. After omega equal 1000 radian over second, the plot becomes flat again, which implies the presence of a zero that cancels the pulse effect. So the next step is we convert the 40 decibel flat magnitude into a linear gain value using the formula dB equal to 20 log 10 multiplied by K. So we put the value into the formula and we get the K equal to 100. So next, for the third step, we need to understand the slope behavior, which is the magnitude drops into negative 20 decibel per decade between omega 1, 102 and omega 2, 103. This suggests a single pole is introduced at omega 1, 100 radian over second, reducing the slope by negative 20 decibel over decade at omega 2, which is 1000 radian over second. The slope becomes flat again, suggesting a zero cancels the pulse effect. So next we go to the fourth step, which is to construct the transfer function. We need to put the value into the again k equal to 100k, a pole at omega equal to 100 radian over second, which is will turn into s plus 100 in denominator. And next we need to enter a zero at omega, which is 1000 radian over second, and it will convert to s plus 1000 in numerator. Hence the transfer function is hs equal to 100 multiplied by s plus 1000 over s plus 100. And we need to identify the simple pole, which is a negative 20 decibel over decade, or omega 100 radian over second. And the final step is to identify the simple zero, which is 0 decibel per decade, or omega 1000 radian over second. It will go to the h omega equal to 100 plus j omega over 1000 over 1 plus j omega over 100.
Hello, I am Hariharan. As the next part, we are moving to the discussion slide. In this assignment, we analyze two core aspects of transfer function using dot plots. For question A, we begin with the given transfer function, which is h omega equals to 200 j omega over open bracket j omega plus 2 close bracket open bracket j omega plus 10 close bracket, where we identify the effect of 0 at the origin and 2 poles on the system's frequency response. By breaking the function into its standard form, we plotted the magnitude and phase dot plots showing clear slope changes at the corner frequencies and gradual phase transitions. For question H, we were given a baud magnitude plot and successfully reverse engineered the corresponding transfer function by analyzing slope changes and estimating the corner frequencies at omega equals to 4 rads and omega equals to 10 rads. This allowed us to construct a realistic approximation of the original system.
So for the conclusion, this assignment really helped us to strengthen our understanding of transfer functions both in forward and reverse analysis. We learned how to create both plots from a given mathematical transfer function and also how to interpret the real both plot data to figure out the original equation behind it. These skills are super important in electronics, especially when it comes to designing circuits, analyzing system stability, filter responses, and control dynamics. We also improved our ability to spot and explain slope changes, corner frequencies, and how phase shifts behave, all of which are the key to predicting how a circuit will perform in real life.